I would like to give a special thanks to my fellow research team. So that includes Dan Gillins, Matt Gillins, and Christopher Parrish of Oregon State University, as well as Eric Kane from ODOT. And I would also like to thank ODOT and PacTrans for the funding, because without it, we would not have been able to do any of this research. So today, I'm going to build off of the previous presentation on using UAS systems for bridge inspection. So I don't really have to cover the motivation, as he covered that very well for me. I thought it was funny that we had some of the similar images there. But yeah, so using the traditional methods for bridge inspections right now, they're dangerous and they cost a lot of money, right? So I don't need to reiterate that. So how do we use UAS systems? Well, they're very beneficial because you can do some visual inspections, preliminary visual inspections from the ground. So you can have your inspectors firmly on the ground and remotely inspecting the bridge. So what is unmanned aircraft systems, or UAS? This shouldn't be confused with UAVs, because UAV is just the aircraft, and UAS is including everything. So it includes your data link, your ground control station, your human operators, your navigation system. Basically, the entire package bundled together is UAS, and that's how the FAA defines that. So looking at different UAS systems, if you guys start looking out into the market to buy one of these, you'll be a little overwhelmed because there are a ton of options. But out of all of those options, they can be broken down into 3 different classifications. You have helicopters, fixed wings, and multi-rotors. Going through these, they all have their different kind of niche where you would use them. Helicopters are great because they can carry a very high payload. So if you want to put, say, one of the small LiDAR scanners on there, you'd want to use a helicopter because they're very heavy. Next is the fixed wings. Fixed wings are great. You can cover large areas, but you're not allowed to just, you can't just hover and take images of a single area. And next you have the multi-rotors. These are very easy to, I guess I wouldn't say easy, but they're the easiest one to maneuver. And you can have various payloads on them. You can still have large payloads, and they allow you to do vertical landing and takeoff, so you don't have the issues with the fixed wings, how you have to have a large landing zone. So for our research, we went through and we selected this UAS platform. This is the SenseFly XM, or now called the Alvarez. What this has on it is it has, in the head, we have an HD video camera and a 38 megapixel still camera. It also has a flash or a headlight, so you can get that lighting effect that you would want if you're in a shadowy area. And it also comes with a thermal infrared camera on it. This sensor head is able to move 180 degrees from straight up, so at zenith, to 180 degrees down at nadir. So you get a lot of motion there. And it also has 5 nav cams and ultrasonic sensors. So these nav cams are positioned left, right, down, back, and then you have a nav cam in the head as well. And that is the same for your ultrasonic sensors. The nav cams can be used to help the pilot see where he's flying. So if you're drifting along the bridge, you're able to look forward to the right and see where you're flying, but you're able just to have good awareness of where your aircraft is relative to the bridge. And the ultrasonic sensors help you by gauging how far off you are from that member. You can also use ultrasonic sensors to lock your aircraft to a certain set distance away, so you're getting consistent and systematic data where you're always at that same distance. Okay, so here's an example of the thermal imagery that you can acquire with this system. Next, we're going to talk about the ground control station. So for this platform, it is operated based off of a laptop. Everything is run through the laptop. Your controller, your data link, everything is connected to this laptop. And here you're getting a live feed from the platform for your video. So you're constantly able to see that. You're able to switch between all your different nav cams. Here you can also plan different missions. So if you want to do manual flights or waypoint missions. So talking about the manual flights, this system has a lot of cool gadgets to it. Depending on what you're going to do, this is good and bad because technology can fail, so you always have to be aware of that. But one of the cool things with this is you can set a certain distance off that bridge, and then it has a coast function, or a coast function where it can just smoothly go at whatever set speed you want to go, from 0.5 meter per second to several meters per second. And then you can set your camera trigger to go from 5 seconds to 30 seconds. And at that way, you're just systematically collecting imagery of the whole bridge, and that ensures that you're capturing all features of the bridge. When you're also doing these manual flights, this is going to allow you to get in closer to certain members. Say you want to go look at a pin connection really closely. You would do that with the manual flight with the sensor assistance on it. The other flight method that we would propose using is waypoint missions. I have a couple examples here of different waypoint missions. In your upper right, that is just a grid pattern, so that's going to give you the topographic features of your area. Next, this one is for if you're inspecting a tower. So you can set this up. Each of these cones that you see here, so each of these individual cones is a camera position. So your aircraft is going to fly to that position, take a picture, fly to the next one, take a picture, and you can have it set to where you want it to be, your camera to be directed. So additional things are, so this is a similar one. This is another grid pattern where you're just getting those topographic features. But what's different about this one is this is showing a safety buffer that you can set. So aircrafts do fail. It's going to happen when you get one. It's just a matter of when it happens. But what you can do here is you can set up this safety donut is what we call it. So this inner ring, what's going to happen is your aircraft, if your aircraft hits that inner ring, it's going to alert you and say, you're leaving your AOI, please return to the AOI. And then you can set this distance out to the second ring, and if it hits that ring, you can have it initiate a safety protocol. So that would be return to launch, or land where you're at, or just hover in place. So there's a lot of different features and safety protocols that you can implement. So in summary of the two flight methods that we use the manual mode with sensor assistance and waypoint missions. The advantages here is the operator can carefully position the camera and view specific features with the manual method. You can go up, get those close-up views, and it takes a little bit less time because you don't have to actually plan those missions out. And then for the waypoint missions, you get these overlapping photos. It's very systematic, and it ensures that you are imaging the entire structure. And I'll get into why it's important for us when we do it. When we want to image the entire structure, there's some cool videos I'll show you. And also, the waypoint mission has less human interaction with your flight. Okay, so this is our second UAS platform that we use. I won't talk about this one too much because this is more of our backup. But this is a DJI S900 that we had built. It has GPS enabled, and we also have two different sensors that we use. We have just a Sony a5000 with only a 3x optical zoom, and then we have this Sony WX500 with a 30x optical zoom. This optical zoom is great if you want to get a further standoff distance. So say you're having issues with wind and you're afraid that you're going to get pushed up into your structure. You can stand off further back, use your optical zoom, and make it seem like you're right there next to the structure. And this way, with the optical zoom versus digital zoom, you're not losing any of that attention to detail, so you're still getting high detailed images. So next, I'm not going to talk about this too much, but before you go out and fly, you need to go out, you need to become approved from the FAA. So OSU is great because we have this COA, we have a department that went through and handles all of this regulation process for us. What these waivers basically say is you need to fly less than 400 feet, AGL, so that's above ground level. You need to be flying in Class G airspace. You need to maintain line of sight with your aircraft, so that means your pilot has to constantly be able to see your aircraft. And the operators have to be certified by OSU. So we just have a 1-week class where you go in and you have to get certified. They make sure that you are able to maneuver the aircraft at a satisfactory level. With these waivers, you can also apply for different waivers that you can, so you can do more complicated flights. So like flying at night, our waiver doesn't currently allow us to fly at night, but you can apply so that you can. And similarly, you can apply so if you want to fly out of line of sight. So if you're using a fixed wing aircraft doing like power line inspection, you would be able to apply for that waiver so that you wouldn't constantly have to maintain a visual of your aircraft. Okay, so to date, we have inspected 5 different bridges. The last fall and last summer, we did these 4, the Independence Bridge, Crooked River Bridge, Mill Creek Bridge, and St. John's Bridge. All of these bridges were flown with manual mode with sensor assistance, with the exception of Crooked River Bridge. Crooked River Bridge, we did do some waypoint planning so that we could construct a 3D model of the bridge. And most recently, this was a couple weeks ago, we went out and inspected Winchester Bridge. I'll have some images here for you guys to see these. So here are a few of the images. You can see cracks in your decks, some pin connections. You can identify paint failure, pack rust. Here's a pin connection, and you guys are able to distinguish where you have touched up with the paint and where you haven't. Here's another pin. Oh, this is a good one. This is on the Winchester Bridge. You guys can see that you have some exposed rebar from your deck. So it's very easy to go through and identify just some of those key visual aspects quickly and efficiently without having to actually go out and climb the bridge. Okay, so this one is also of Winchester Bridge. Again, and you're just able to go through. This is great if you want to just go through and see, make sure there weren't any missing bolts on any of those connections and things like that. Okay, so this gets into the more technical side of it. You've went out, we've collected hundreds of photos of all these bridges, so what can we do with it? Other than just visually inspect all the images, let's go ahead and bundle them together, and this is where structure for motion comes in. This is a relatively new photogrammetric technique, and it leverages some computer algorithms from computer vision, and it's really great for making a 3D model using different cameras and just consumer grade cameras, which makes it great for implementing with UAS imagery. So the way this works is you have this algorithm, it goes through, it matches key points in all of the images you've taken, it aligns those together, and while it's doing that, it is recovering the camera parameters, so the orientation of where that photo was taken, right? So you're getting the roll, pitch, yaw, and the XYZ location. After you've done that, it goes through, it does a bundle adjustment to kind of hone in on those parameters, and then you are able to output a dense point cloud, 3D point cloud, or an ortho image. So in order to do that, you need to go through and set control. You don't need to, but it is recommended. So to make this 3D point cloud, if you don't have any established control in your site, the scale is going to be off. So you're not going to be able to measure any real values on your model. So to do this, we set up some aerial targets, as well as we used a total station to measure locations of photo identifiable features on the bridge itself. So as you can see, we took pictures through the total station of the pin connection, and there's our aerial target that we occupied with GNSS. Okay, so I have this cool video fly through of the point cloud that we generated. There's a couple different programs, and there's becoming more and more programs that you can generate these point clouds through. Without much knowledge, you can do this. They're very easy to use. Obviously, they're kind of a black box software, so you want to do your research and make sure you know what you're doing, though. Got a little shaky there. But, I mean, it's very easy to identify. You guys can see all those cross members. And after the video, I'll show you guys some still images so it's not so shaky. Okay, so this is where that fly-through was created in this program. This is an open source program called Cloud Compare. There's a lot of little web seminars on how to use this program if you guys are interested. That is available, and like I said, it's open source, so it's free. You guys don't have that expensive cost of buying the program. Okay, so just looking at some of these images, you can see a lot of those cross members. You're getting a lot of good detail out of it. With this point cloud, you could export this into, say, a CAD or a BIM software and actually make those 3D models into solid objects. So here are some more images here. And like I said, you can make an ortho photo. So what this is doing is it's making this giant mosaic of all of the images you collected of the bridge. And this way, what you're doing is you're having a scaled image that you can go in. It's very high detailed. I could zoom in on one of these bolt patterns and it would be very clear. I could zoom in on that and it would be clear. It wouldn't be all pixelated like you would if you just took a photo from this far off, right? And this is possibly the coolest part of making this point cloud, is it organizes all of your images. So now if I want to go through and I wanted to inspect this bridge after I made this 3D point cloud, I could go through and just click certain points, and it's going to pull up on the right over here all of those photos that were used to generate that point, right? So now it's very easy for me to just go through and say, okay, I want to look at this pin connection. Now I can go through and look at all of those photos, and it's just an easy way to manage your data. Like I said, you end up with hundreds of photos from one inspection. So this is a very good tool because it's difficult to go through and navigate through all of your photos. Okay, so challenges. We want high resolution photos, but proximity to the structure degrades your GPS signals. So there's two things that you can do. You can use a camera with an optical zoom. That way your standoff distance is better, so you're not getting that degradation. Or you can just fly without GPS, right? That's a little more difficult and it's going to require more training, which I recommend you definitely have because your GPS will go out on occasion, so you want to be able to fly that manual mode. Next, you have wind pushes you up against the aircraft. So what you can do is you can use a heavier aircraft so it can't be pushed around as easily. And you could also use that optical zoom camera to get that standoff distance once again. Too little or too much light degrades photos. So as you're taking these images, especially if you're going to be making a 3D model, it's going to be very sensitive to under or overexposure. So what you can do is you can plan flights when the sun is directly overhead, or what I prefer is planning a flight when it's going to be completely overcasted. That way you're getting consistent light throughout your scene. You're not getting any areas where it's going to be under or overexposed. But you can also do some real-time camera aperture changes. So that's just changing your black-white balance, things like that. Conclusion and future work. UAS imagery could be beneficial to a bridge inspector in identifying visual defects. I would want to iterate this, that this isn't a tool that can replace the inspection. I mean, there are still going to be the inspections where you need to be at arm's reach. You need to do some probing, some scraping, things like that. So this is just a tool to go out and visually do some preliminary inspections and see where you need more in-depth inspection, right? Studies testing different bridge types as well as other UAS are constantly ongoing, and I think this is going to be the case for years to come. Developing recommendations for implementing UAS in structural inspection. This is also going to be something that is constantly happening. These different recommendations are going to be changing based on the technology that comes out. And lastly, I would like to give some more acknowledgement to ODOT and PacTrans for funding all of this research to date. I would like to thank Matt Gillins, who provided most of this presentation. Eric Kane at ODOT, he's been a great resource for us, as well as Joe Lee and the ODOT TAC Committee, as well as fellow OSU graduate students such as Free Javanejad, Corey Kellum, and Richie Slocum, who have assisted me with a lot of these flights.